this example, we're looking to find the line integral of FDR, where C is this curve drawn below, so it's kind of this squiggly path between -1, 4 and 1, 2. And then F is the vector field 2xyi plus x squared minus yj. Now, obviously, this curve looks terrible, so we're hoping that we don't need to find a parameterization for it. So we might already start to think about this idea of, well, could we apply this fundamental theorem of line integrals? So let's try and take a look at F and see whether or not it is a conservative vector field, because if it is, then we've got lots of options, which is nice. So is F conservative? So let's take those partial derivatives and find out. So the partial of m with respect to y, so the x component with respect to y would be the partial with respect to y of 2xy, which is going to be 2x. And then the partial of n with respect to x, so the partial of the y component with respect to x is going to be the partial with respect to x of x squared minus y. So the x squared is going to go to 2x, and the y term would drop out to 0 since we're doing an x derivative. So indeed, they are equal. So yes, it is. So we can use the fundamental theorem of line integrals, because we can also see that our curve C, while it is kind of a funky curve, it is a smooth curve. So it does have all these continuous partial derivatives at any point, which is good. So we can use this fundamental theorem. So let's use it the way that we did before, where let's look for that potential function. So let's find the potential function, which we'll call a little f. So let's take, we would have little f of x is going to be the x component, so 2xy, and then the little f sub y would be the y component, which is x squared minus y. So then let's take a look at these two pieces. So let's integrate f sub x dx, which is going to be the integral of 2xy dx. So we're really going to increase the power on x, which will go to x squared, and divide by that power, so we'll end up with x squared y, and then plus some function of y. And then we need to do the same thing with f sub y. We could also alternatively take the derivative of that function we just got with respect to y and compare it to the f sub y. But I'm going to do it the other way for this example. So f sub y dy is going to be the integral of, let's see, x squared minus y. Erase that quick. Dy, which x squared dy is going to become x squared y, and then minus y will become minus y squared over 2. And then we've got plus some constant function of x. So now we want to equate those two functions and look at for what would g of y be. So we can see g of y would need to be this y term that shows up that we don't have up top, and then h of x is just going to be plus a constant. So the g of y would have that plus a constant as well. But then otherwise we've got the x squared y term in both of them. So f of xy is going to be x squared y minus y squared over 2, and then plus some constant c. So then taking a look at our line integral that we want, we need to do the line integral over c, which remember this is our curve C up here, of that capital F dr. And rather than compute it as a line integral, we're going to do it in terms of that potential function. So we're going to say that this is equal to the potential function, which is x squared y minus y squared over 2. I really don't need the plus c because we're going to do a subtraction. And we're going to evaluate that from the initial point, which it is important to note the orientation of this curve, right? So that makes this the initial point, and this one the terminal point. So we're going to do it, the bottom one is -1, 4, and the top point is 1, 2. So we'll evaluate it at 1, 2 first. So that means that we're going to have 1 squared times 2 minus 2 squared over 2, and then we'll subtract off, plugging in -1, 4, so we'll have -1 squared times 4 minus 4 squared over 2. So it very much has that feeling of take that kind of antiderivative function and evaluate it at B and then subtract off evaluating at A. So we have 2 minus 2 squared over 2 is 4 over 2, so that's minus 2. And then -1 squared times 4 is 4, so we'll have minus 4. And then we'll have plus 4 squared is 16 divided by 2, so we'll end up with 8. So these 2's cancel, so we have 4. -4 plus 8 is +4 for this line integral. So notice we never needed to deal with a parameterization for c at all. We just instead found the potential function of capital F.